Kirchhoff's current law says that the sum of the currents at any node is 0. Okay, let's draw an example to explain what we mean by this. So if I had some circuit element connected like this, by the way, this little kind of squiggle thing like this is how we draw a resistor. So if I have a resistor connected like that, and maybe I have another one here, and maybe I have another one here, and then these are connected to sort of the rest of the circuit, right? So this is kind of just a small section of some larger circuit diagram. Then I could label on here some currents. So I could call this, say, I1, this one here I2, and this one here I3. Kirchhoff's current law says that these currents must add to 0. So here, sum of the currents must be 0. So in other words, I1 plus I2 plus I3 is equal to 0. And this is basically a mathematical way of saying that charge is conserved. So charge is conserved. So from a physics point of view, that means that electric charge can't be created or destroyed, right? It's always just moved from one place to another. So charge is conserved, so that means that we have this balance. We have basically in equals out, or in a kind of mathematical engineering sense that the sum of the currents would be 0. Some will be positive, some will be negative, so there'll be some currents flowing in, some currents flowing out, but together it must all add up to be 0, so that total charge would be conserved. So this concept of a node is really worth explaining a little bit more. So a node is something like this in the circuit, where we have multiple components kind of coming together. But they can be drawn in a variety of different ways, so it's important that we recognize kind of what parts of the circuit make up a particular node. So as an example, I could take that same circuit that I have just drawn above, and I could do something like this. So I could take resistor, let me give these names, R1, R2, and R3. So I could put R1 kind of like this, and then I could put R2 over here, and then I could put R3 over here. And this is the same circuit, right? Because I have these 3 resistors which are all connected together in one place. So it doesn't really matter how I draw it, the node makes up all of this part of the circuit where these perfect ideal wires connect together I guess I'll call them the top sides of these 3 resistors. So this is a really important point to understand. This is the same circuit, okay? It's just drawn differently. And so when I calculate Kirchhoff's current law for this case, I would have here I1, I2, and I3, and I recognize that they all feed into the same node. So here, this is one node of the circuit. One node because all of this part is connected by these ideal wires. So that makes it all a node. So the node is just all this part of the circuit that is all connected together by these wires. And so again, for this particular case, I have sum of currents equals 0. This is Kirchhoff's current law. Sum of the currents equals 0. I1 plus I2 plus I3 would be equal to 0. Now, depending upon the rest of the circuit, so whatever else these bottom nodes here are connected to, would then dictate whether some of these currents were positive or negative. So some would be flowing in, some would be flowing out. But they must add up to 0 in the way that it is labeled here. Now, another important point to recognize is if some of these currents were labeled the other way around. So let me do an example. I'm going to change this one here. So if I had written I3 the other way around, going down, okay, I3 going down, then I need to be really careful about the negative sign for this, because these currents now point in opposite directions. So here, when I write Kirchhoff's current law, so KCL, Kirchhoff's current law, the way that I would write this is so two ways, right? I can say kind of sum in equals sum out. You might prefer to think of it like that. So the sum of the currents flowing in will be equal to the sum of the currents flowing out. So as the way that they're labeled here, I can see the currents flowing in are I1 and I2, and the currents flowing out is I3. So you might prefer to think of it like that. Or you could just write sum of the currents equals 0, and then as you go around and find all of those currents, you just pay attention to which way around they're written. So you could say, okay, I1 and I2 have a positive sign because they're flowing in, but I3 has a negative sign because it's flowing out. And of course, this is the same thing algebraically, right? You can kind of look at this equation and see that they're the same. And it doesn't really matter which strategy you use to go and write it down, but it's very important that you pay attention to the polarity with which these currents are drawn. So let's do an example. So suppose I have this particular circuit diagram here. So I have two current sources, so that's here and here, and I have two resistors. So I have a 100 ohm resistor and a 200 ohm resistor. So let's have a look at how we would actually go about calculating the current I0. So I0 here is what I'm asked to find. That's the objective of this problem. So the first thing that I recognize is I have actually a few different nodes in this circuit. So I have a node here, I have a node here, and I have a node across the bottom here. So this circuit contains 3 nodes, and I can write Kirchhoff's current law for all 3 of those nodes. So that would give me 3 equations that I could work with. But it so happens that this one is kind of fairly straightforward, and I can really get away with just writing KCL once for this particular circuit. So let me explain that. So if I look specifically at this node in purple, then I know the current flowing in on this branch. I know that that's 2 amps because I have an ideal current source. The resistor here cannot change the amount of current. There's always 2 amps because of that ideal current source. And similarly, I know on the right-hand loop, I know that I have 3 amps, again, because I have this ideal current source. So what I can do here is I can think to myself, I will write Kirchhoff's current law at the node indicated. So the one that I highlighted in purple. So here I would have sum of the currents flowing in must be equal to sum of the currents flowing out. So the currents flowing in, looking at my diagram, I have 2 amps and 3 amps, and the current flowing out is I0. So I have 5 amps is the current that is in I0. So I should write that as 5 amps, put the units there. So that's an example of using Kirchhoff's current law to actually analyze a circuit.